Uh, Thank you. So I'm going to talk about a 2018 paper. It's in Communications and Math Physics. Here, archive link. It's by Brubaker, Buciumas, Bump, and Gustafsson, all of whom are usually, but not today for some reason. So this is kind of an old paper, but we know more now than we did this, so this can be. So I just want to talk a little bit about the boson-fermion correspondence. And this is something which came out of mathematical physics. So origins in mathematical physics. One is at the time dual resonance, but now it's been sort of subsumed in conformal field theory and string theory. And the other is soliton theory. So in the dual resonance theory, there's of course a lot of history to that, but the papers that Kac cites relevant to this when he talks about the boson fermion correspondence are by Sturm and by Mandelstam. So I guess those are the ones that we should quote. And it leads to a purely algebraic fact, which I'm going to talk about a little bit. So the first thing that was noticed, if you study the basic representation of affine Lie algebras, really extend to the Vertex Lie algebra also, the concrete by operators, which are called vertex operators, and depending on where you look, they can look quite different, but they'll appear in this talk. And then the mathematicians started looking at it, and the two papers where this mentioned were a 1981 paper of Kac, Kajdan, Lepowski, and Wilson, and then a paper of Igor, Frenkel, and Kac, which gave instructions of representations of affine Lie algebras. And there's one particular representation of an affine Lie algebra that will appear today. So this this was when the mathematicians started looking at it. But now, meanwhile, in soliton theory, starting with Sato, but by Jumbo, Date, Miwa, and others, Kashiwara, and so forth. In soliton theory, you have the Cordova-de Vries equation, and then the KP hierarchy. These are solutions of differential equations that have an intricate algebraic structure, which they started uncovering. It led to the same. So then the boson correspondence was treated algebraically in a book by Katz and Reina called The Bombay Lectures in Infinite Dimensional Lie Algebra. It's a great book. It's a little well, anyway, there's a. So I'm going to talk about the boson-fermion correspondences. They explained it. General, one of the main examples is one that I'm concerned with today, started by Kashiwara, Miwa, and Stern, actually started in Stern's dissertation in Reshetikhin. And then this is a realization of a representation of an affine Lie algebra, the basic representation, which is quite important in different things, including not only conformal field theory, but things like the representation theory of the symmetric group. And this was taken up by Lascoux, Leclerc, and Thibon. They worked on the boson-fermion correspondence. Everything was axiomatized by Thomas Lamb in his thesis, which appeared in a few papers. So those are important references. So the key thing is that a Heisenberg-Lie algebra, in some sense, a Heisenberg-Lie algebra has a unique representation with prescribed central character. That's a reflection of a fact, the Stone-von-Neumann theorem. Formulation is the following fact. So you define this Lie algebra. It's spanned by generators bk, one for every element of z, and then another generator I. B0 and I, for the identity, it should act by one in any representation that you care about. These two are going to be central, and the other have satisfy this commutation relation, that if you take the commute bk and bl, that you get 0 unless k is equal to minus l, and if they are equal, then you get k times the identity matrix. So I'll say that a representation is a highest weight representation if it has a vector which is annihilated by all the positive b sub k's. And then b0 and I will act by scalars, and I'm going to assume that I acts by identity. So we can ask for a possible representation with highest weight vector, and that is unique if it exists. Such a representation will be called the highest weight representation, and there's a unique one. This is, you can find proofs of this. It's not hard to prove. You can find proofs of this in the book of Katz and Reyna, or in Victor Katz's book, Infinite Lie Algebras. So the idea is that we'll give different representations of the Heisenberg-Lie algebra. So the first one is on the bosonic Fox space, which is the ring of symmetric functions. The ring of symmetric functions, polynomial ring in the elementary symmetric functions, which are given by this formula. I also want to talk about the power sum symmetric functions and the Chord polynomial, or the Chord functions, which are indexed by partitions. The Chord functions form a basis of this ring as a Z module. So now we can define an action. If we extend the scalars to Q or to C, then a polynomial ring in the P sub k's, k being greater than or equal to 1. And so you can define operators, multiplication by P sub k or differentiation with respect to P sub k. And this is the bosonic. Are there any questions? Okay, then the other realization of the Heisenberg-Lie algebra is the fermionic Fox space, and this is motivated by the theory of the electron. So Dirac discovered the Dirac equation. It's a Hamiltonian. It has for an electron, it has energy levels which are quantized, but they're very small negative energies, and it's a problem because you could imagine that if an electron is a solution to this equation, it could radiate an infinite amount of energy just by dropping to lower energy levels, and that's unphysical. So the solution that Dirac proposed was that the low energy levels are all occupied. So I'm going to represent the occupied states by black dots, and the negative energies will go off to the positive energies are going to go off to the left. And so, so the assumption is that all sufficient energies are going to be occupied states, and the highest energies are going to be unoccupied. This is called the Dirac sea. Now, to represent in this Hilbert space, we start with another vector space, for every energy level, and then we will take the wedge of all the vectors in the occupied states, and that's a basis vector representing a state of the system. And now the wedge is interpreted as 0 if any vector appears twice. And of course, if you interchange two vectors, then you expect it to change sign. So then you can index the states of the model by partitions. If I have a partition, then I can turn it into a set of distinct integers by adding m and then m-1 and so forth to the indices in the partition, which are eventually 0. And so, for example, f-1, the Fock space of level 1, level -1, of charge -1, you can imagine moving this vector into this state and this vector into this.
Dan, we're losing, or at least I'm losing your audio a little bit.
Same here.
Well, I will kill my video, and then you won't see me. But unfortunately, this happens. You could lose me completely, and if that happens, it's Verizon's fault. So, if I disappear, I will return. Are there any mathematical questions? Okay, so if you take the empty partition, then you get the vacuum, and the vacuum of charge m, it looks like this. This is the vacuum of weight 0. And more energetic states can be obtained from the vacuum by applying operators that bounce you up to a higher energy level within the same charge. And then later we'll encounter creation and annihilation operators that change the charge, and those are fermionic. So the operators work like this. So we can have an operator that adds -k to the energy of a state, and that will be called sub k. So if you apply that to a wedge, what you have to do is you have to sum over all possible i's of applying the operator to the ith component. I think there's a yes. Okay, I thought there was a typo. There is a no. There's no typo. So, for example, if you applied b-2 to the vacuum, you would find exactly two ways of doing this. You could add it to the 0 component, or you could add it to the -1 component. If you add it to the -1 component, then you have to switch two vectors, and this produces a sign change, so that this actually has one term appearing with a plus sign and one term appearing with a minus sign. But you'll find that there's only finitely many terms which are 0, because most terms will have a repetition, and so this looks like an infinite sum, but it's actually finite. Okay, now these operators satisfy the same relations as the vectors in the Heisenberg Lie algebra. So we have we have two realizations of the Heisenberg-Lie algebra, since the module of the Heisenberg-Lie algebra is unique, there's a intertwining operator from the fermionic Fox space to the bosonic Fox space, and this is the boson-fermion correspondence. And then one of the theorems, which is proved in the book of Katz and Reyna, is that this takes the basis vectors of the semi-infinite monomials to the Schur polynomials. Now, there's another part to the boson-fermion correspondence that they proved, and I have to explain that. But first, let me introduce some other operators. These are the fermionic operators. So first of all, if I have a vector in the space V, I can just wedge that with a vector, and I will obtain either 0, or I will obtain another basis vector, possibly with a minus sign, because this V might have to be moved out. So I'll use alternative notation, and I will use UI check is okay. The alternative notation is on the next slide. So anyway, if I have a linear functional on V, then I have a lowering operator. That if I apply that to a wedge, what I do is I go through and I find all places where I can possibly apply that, and this then I will remove that vector and just replace it by the scalar. So again, if this is a basis vector, there's exactly one place that I can apply that in a wedge. So this is looks like an infinite sum, but it actually has at most one term. So then I can package these operators by formal generating series. So this is the generating series. I'll call it X of t for the raising operators, for the creation operators, and then this is going to be the generating series for the lowering operators. And then what they prove is that if you take these operators and you transfer them to the bosonic Fox space by means of the boson-fermion correspondence, that you get operators that look like this. And the reason I'm showing you this is that we're going to see similar looking operators through the rest of the talk. So these operators all commute with each other. These operators all commute with each other, but these operators do not commute with these operators. I hope you can see that my cursor is being used to indicate things. So we can take this sum and we can apply an exponential, and then this would decompose as a product. And we can do the same thing to this sum, but we cannot, we have to be careful if we want to interchange these operators and these operators. And the important thing is that we do the lowering operators first. So if you had some vector and you applied the raising operators first, then you would get some kind of an infinite sum, and things would be much messier. You can avoid divergences by being careful and always doing your lowering operators first. So that's a procedure which is called normal ordering. So I like to write it this way. It's actually possible to compute the commutator of these two expressions, but these are well behaved because they push things into the vacuum. They tend to annihilate things, where this produces some infinite sum of things with arbitrarily high energy levels. So this expression is problematic, and it's very useful to do all your annihilation operators before your creation operators. we're going to call these types of operators and these types of operators half-vertex operators. And only the second one is really an operator, because the first one, if you apply it to a vector, produces an infinite sum with arbitrary high energy levels. And these operators almost commute. So that means that I can regard this as a unit. I can regard this as a unit. I could expand the exponentials as a product if I want. Okay, so the slides are repeating what I said. Are there any questions about these operators or normal ordering? So what I've tried to show you is that they appear sort of naturally. And then the thing is that if you look at these papers, such as the paper of Frenkel and Kac, where the representations of the affine Lie algebras were constructed, these operators appear throughout the paper, these kinds of operators. So although we have to be very careful about how we treat these as operators, this one is not so bad. If we apply it to a state, we get just a finite sum of states. This one, we get something which is slightly crazy. But at least if we took this and we extracted the coefficient of one particular vector, that you would get a finite sum. So although this is a little problematic, if I take these 2-point functions, those actually do make sense. Now, remember the fermionic operators. This is wedging with a basis vector for the vector space V. This is contracting with a vector for the vector space V. These these satisfy these relations, that they form an infinite dimensional Clifford algebra. And you can try to realize the bosonic operators in terms of these operators. Be very careful about how you write B0. You have to write it so that if you apply it to a vector, that at least infinitely, for all but finitely many times, the lowering operators are going to be applied first. Now, if you contract with a vector of high energy, that's a lowering operator. Or if you wedge with an operator of negative energy, that's a lowering operator. So this is the right way to do that. So we're going to talk a lot about the Q-Fox space. This is a realization of the basic representation for UQ of SLN hat. And there is a boson-fermion correspondence. And Lascoux, Leclerc, and Thibon used the Q-Fox space to define what they called ribbon symmetric functions. And I will give the definition of these later in the talk. And we will encounter things which are closely related to those. One of our points is that metaplectic Whittaker functions, which is the topic that led us to this subject, are closely related to LLT polynomials. And then Lamb, in his thesis, which was published in a few papers, gave an axiomatic theory that applies to various settings, including the Hall-Littlewood, McDonald, and LLT polynomials. So there's a Cauchy identity. I know that people in the seminar are interested in Cauchy identities. In any of these examples, there's Cauchy identities and Pierre rules. Now, the KMS theory is a Q-deformed theory, so it's quantum. It's more quantum than the vertex operators that first appeared in string theory. Even though string theory is a quantum theory, it produced these operators, and they were not Q-deformed in the way these operators are. So the Clifford algebra hasn't really been, as far as I know, and maybe some people can correct me, but as far as I know, the Clifford algebra hasn't been fully brought on board in the Q-deformed theory. And so in our paper, we used the creation operators, but we avoided the annihilation operators. And then I just want to say a word about vertex algebras. So Borchards was interested in ideas of Frenkel, Lepowski, and Merman, who were trying to construct the monster using vertex operators. But he worked on the algebra, and he obtained a purely algebraic context for the vertex operator in what he called vertex operator algebras. And then the theory was streamlined by people like Katz and Dong and Lepowski, and so the current theory looks a little bit different than Borchards' original version. He applied this to the monster and was able to prove the moonshine theorem, which of course was why he got the Fields Medal. So so there are different kinds of vertex algebras. There's a book by Edward Frenkel. That's a different Frenkel than the Frenkel that was mentioned here. There's a book by Edward Frenkel and David Ben-Zvi about vertex algebras, which is I think quite a good treatment of that. There are realizations of vertex of the Virasoro algebra and related representations, the Heisenberg algebra and related representations in vertex algebra. So the ones that most resemble the ones which we're concerned with are lattice vertex algebras. So if you have a lattice, you can build a vertex algebra. If you start with the root lattice of a Lie group, then you get the things like the basic representation of the representation. If you start with the Leech lattice, then you end up with things that can be related to the sporadic simple groups. In our case, the lattice is just Z. So I'm talking about the vertex algebra context for the operators that I already talked about a little bit. Are there any questions or comments? Okay, so if you have an affine Lie algebra, then you have the fundamental weights, and there's one which is distinguished. This is called the affine fundamental weight. It's usually denoted lambda 0, and if you take the highest weight, the integrable highest weight representation with this weight, this is the basic representation. It first appeared in string theory and in soliton theory, but later it was realized, I guess, by Lascoux, Leclerc, and Thibon, that work that people like James and Kashiwara were doing on the modular representations of the symmetric group were closely related to the crystal of the basic representation. So now this is a fundamental part of the representation theory of the symmetric group. And there's a particular realization of this, which is called the KMS Fox space. I'm going to show you what it is. There's another paper around this time which also produces Q-deformed vertex operators in a similar context. And a lot of the formulas in Jing and Misra look a lot like things that I'm going to show you. So I have to at least mention them. So I'm going to call the bosonic operators, I'm going to call them J sub k instead of, so what I want to do is I want to take, so I called them B before, I'm going to call them J now. What I do is that I take one of the vectors and I'm going to denote it by n times k. N is a fixed integer when I do that, the terms may be out of order because this could be pushed to some lower energy state and I might have to switch it with this. And the caveat here is that the rule for interchanging some vectors is more complicated than you might think. You might think, well, you change the sign and maybe you throw in a power of q, but actually they're correction terms. So so I have to unravel what this means, what this wedge means, and if L and M are equivalent modulo n, then I interchange them. If they're not, then there are a finite number of correction terms. And I'm going to use this occasion to slightly generalize their setup. I'm going to throw in these functions g, which have been called Gauss sums in previous lecture, even though they're actually just indeterminates at the moment. There's only a finite number of terms here. And I guess I don't want to dwell too much on this rule, although it's important, in fact, essential. It's not so necessary to talk about it. Well, answer questions.
I guess in this formulation, Dan, you've used V for your parameter instead of Q.
Yeah, the parameter V is now called V. Q is V, let's see, V is Q squared. So if a Q appears, V is Q squared. Okay, now before I come back to this, I want to talk a little bit about LLT polynomials, and they can be given a tableau theoretic definition. So I want to tell you how that works. So an N ribbon is a skew shape that's connected and doesn't contain a 2x2 square, and has size n. And if you have a partition, so in the example it's 664411, here's its Young tableau, I can start removing ribbons. And it doesn't matter in what order I do that. There would be different ways of doing that. When I'm done, when I end up with, which doesn't, oh, this is, yeah, I cannot remove any more ribbons because I would have to remove the top vertex. So I'm done at this point. So this ribbon that's left over is called an n-core partition, or a 3-core partition in this particular example. So if I have a ribbon, then I consider its height and I subtract 1. So this ribbon has height 3. So the spin, which is the height minus 1, is equal to 2. This has spin 0. This has spin 1. This has spin 1, this has spin 1, this has spin 0. I'll need this definition in a minute. Now I call a skew shape, there's a typo here. I call a skew shape a horizontal n-ribbon strip if it can be decomposed into n-ribbons such that the top most right box of each lies on the top row of the skew shape. So the top row boxes are, if you can see my cursor here, that's at the top. Here, that's at the top. Here, that's at the top. So this skew partition is an n-ribbon horizontal strip. Now, an n-ribbon skew tableau is a sequence of partitions. And as usual, I'm going to make a tableau because I'm going to take the Young diagram and I'm going to fill in the difference between two of these partitions with 3s and then 2s and then 1s. and each of the skew tableaus is a horizontal n-ribbon strip. So this is the definition of an n-ribbon skew tableau. So the LLT polynomials will be sums over these gadgets. And the spin is going to be the sum of the spins of the constituent ribbons. So in this case, the spin is 5. That's 3 plus 0 plus 1 plus 1 plus 1 plus 0. And the weight is going to be 1, 3, 2. If you calculated the weight as a regular tableau, the weight would be 3, 9, 6. And so I just divide that by, because there are going to be 9 2s, I would divide that by 3, which is n. And then the LLT polynomial is a sum over these shapes. I take q to the spin, and then I take z to the weight, and these are the ribbon symmetric functions. And they have Cauchy identities and Pierre formulas. But I want to give another definition of this, which is I have these bosonic operators. They satisfy relations of a Heisenberg-Lie algebra, except that the factor that you get when you commute j and minus j is different. I have this factor here now. And then it can be shown that if you apply, so this is going to be a half vertex operator. I'm going to take this gadget and I'm going to exponentiate it. I'm going to apply it to this vector, and then I'm going to extract the coefficient of mu. This makes sense because these are lowering operators. It's necessary that lambda and mu have the same n-core. Otherwise, this would just produce 0. Okay, so the theorem is that this produces the LT polynomials. Now, I don't know lattice model representations for LLT polynomials, but there are modifications which Lamb calls super LLT polynomials, and one instance of those look like this. So I'm just going to take this operator that we had before, and I'm going to put a 1 minus v to the k in there, and then I get something which, again, these are lowering operators. The j sub k's are lowering operators because I'm going to take k to be positive, and I can apply that to lambda, and I can extract the coefficient of mu. And then the fact is that this is a representation of the LT polynomials. I don't think that this formula appears in Lamb, but it's easy to deduce from results which are in Lamb's paper, and we put a proof of this in our paper. But our paper doesn't really, oh, no, I'm sorry. I was talking about this formula when I made that remark, but actually it applies to this also. These symmetric functions do appear in Lamb's paper as as things having 2 spectral parameters. But the 2 spectral parameters that we're going to take are he calls z and w, and we're going to just take w to be a multiple of z. I think b times z, and then so these are a variant of the LLT polynomials that Lamb would call super LLT polynomials, and they're closely related to metaplectic Whittaker functions. And what I'm going to show you is that they have lattice models, and that there's something to be said about those. Any questions? Okay, so there's both lowering versions and there's raising versions, and if you took the 2 of them together, you would get something that looked like a vertex operator. So, if I exponentiate this, I will get what's called a half vertex operator. So what I'm going to show you is that we can use these, that we can relate these to row transfer matrices of lattice models that we arrived at by some different route. Any questions? Okay, now I guess I want to back off a little bit and talk about why do we think this is important. So in the paradigm of lattice models, going back to Baxter and the explanation of Baxter's work, particularly by Drinfeld in the theory of quantum groups, the idea would be that you would associate to each edge in a planar graph a module over a quantum group. And then there will be Yang-Baxter equations that will allow you to the integrability of the model. And we've seen lots of examples of that in the seminar series. And the ones that I'm concerned with are ones whose partition functions include spherical metaplectic Whittaker functions. Nowadays, we would try to do this with Iwahori Whittaker functions, but we can just start with the spherical Whittaker functions. We found these models in 2016, and then we are going to try to reinterpret them a little bit today. There's an R matrix, and the R matrix tells us what is the quantum group. The quantum group is this Lie superalgebra. It's quantum affine GL1n. And the horizontal edges of the model can be identified with the n+1 dimensional graded standard modules of this Lie algebra. There's one for every spectral parameter, which would be a complex number. And so this fact accounts for the Yang-Baxter equations, which we need. But the R matrix in this story only attaches to a pair of horizontal. So here's a picture of the R matrix. If I attach that to the grid, then it will attach to a pair of horizontal edges. It doesn't see the vertical edges at all. There may be other Yang-Baxter equations that see the vertical edges, but these do not. So the question is, how do the vertical edges fit into this story? Well, the horizontal edges themselves do see the vertical edges, and we would like to interpret the vertices of the grid itself as R matrices. So what's missing is an interpretation of the vertical edges of the model as modules for a quantum group. So we're going to propose a kind of a solution to this that will take not just a single vertical edge, but we'll take the entire sequence of them. And we're going to interpret those as parameterizing vectors in an infinitely wide grid. So this will be the Kashiwara Miwa Stern Fox space. Let's see, I think I'm going to skip this slide and come back to it. So, so let me start talking about the models themselves. So I want to consider an infinite grid. It's infinite in both directions, but all but finitely many vertices are going to have Boltzmann weight 1. So for this reason, I want the horizontal edges to have pluses for all but finitely many vertices. So if you go to the right, you get pluses. If you go to the left, you get pluses. For the vertical edges, if you go far to the right, you are going to find only occupied states. So those will be indicated with the colors. I have a palette which consists of n different colors. I'm going to call those colors 0 up to n, actually n-1. And if the state is unoccupied, I will just represent it by a plus. Now, then the Boltzmann weights will be such. So for example, here are the Boltzmann weights. You see, if I have two pluses, I have either this state or I have this state. In both cases, the Boltzmann weight is going to be 1. So all of these vertices going off to infinity on the rightmost direction, or all of these vertices going off to infinity in the leftmost direction, they have Boltzmann weight 1, and so that the Boltzmann weight of this state, you can imagine there's several rows, and I've only drawn you one. The Boltzmann weight is going to be a finite product times a bunch of 1s. So that's a property of the Boltzmann weights. Where I have a crossing, the Boltzmann weight is going to be one of these Gauss sums. And sometimes I will have spectral parameters. There's another flavor, which I call gamma ice. Now there's a distinction between these, that if I look at a state of the delta ice, then I think of this as being a row transfer matrix taking this vector. If you can see my cursor, that I'm running my cursor along the top row. The vector corresponding to the top row will be mapped to the vector in the lower row, and these with these Boltzmann weights, I'm always mapping to the right. So so if we think of this in terms of the Fock space, I'm moving to lower energy levels. This I call delta ice. And this one is problematic because it is taking you and you're moving to higher energy levels. So you would if you think of this row transfer matrix as an operator, this is taking an operator to some of states, including things of arbitrarily high energy. Just like the operators that I called raising operators or creation raising operators in the Fock space. Okay, and then the theorem is that the row transfer matrices for these models are half vertex operators for these operators here. I'll say just about a word about the proof. So I am going to make use of the fermionic raising operators, but I'm not going to use the lowering operators. We had a lot of trouble with the proofs, and we found a strategy that worked, that avoided the lowering operators. So so there may be a different way of doing things, but the raising operators you just wedge with u sub k, and then kind of because this is a lowering operator, it's not too surprising that if you commute that with j sub k, that's the same as this lowering operator. So this identity is not very surprising. And then with some energy, then I want to take two of these operators. I'm going to take the I'm sorry, there's a typo here. This should have an asterisk, and this should be a C. So if you can imagine, the correct formula is C sub k asterisk and C sub k minus n asterisk. So then there's a little bit of algebra that says, that is based just on this formula that shows you that if I take these operators, which are supposed to be the delta row transfer matrix, and then I conjugate this by this, I get the same operator, but the parameter has been multiplied. Okay, I'm sorry, there's typos on both sides of this formula, but if you want to see how it should be, the paper is here. This formula. This formula should look like this. I will fix it up. I'll fix the slides a little before I send them to Slava. So the key step in the proof is to show that the row transfer matrices satisfy the same relation. And here the parameter is supposed to be z to the n. And so what does this operator do to a state? Well, it changes it in at most 2 places, and this changes it in at most 2 places. So what this means concretely is if I cut the state apart, I can just work with a little chunk like this, and I'm going to have 4 terms, 2 on the left and 2 on the right. Some of them might be 0, and there's only 4 places where there are changes, and so I get an algebraic relation. There's the way we did things. There's 32 cases, and each of them can be checked by hand. So so you can prove it this way. Any questions? Okay, so I have one more slide, which is about precursors to this. So the oldest work here that I mentioned is Baxter's work on the 8-vertex model. So Baxter solved the 8-vertex model. The field-free 8-vertex model. He showed how you can use the Yang-Baxter equation. It's a parameterized Yang-Baxter equation. The parameter group is an elliptic curve. This was very difficult work. He did it on a boat. He rode a steamer. He tells about this someplace that he rode a steamer from India to England, and he took over the map room and he filled it full of equations and papers. And when he got to England, he had theorem in it. So and as a byproduct, he got the integrability of the Hamiltonian for Heisenberg spin chains. And so there's a relationship between Hamiltonians, which can be thought of as being something like vertex operators, and row transfer matrices. Essentially, the Hamiltonians are logarithmic derivatives of the row transfer matrices. And I'm not sure exactly what I should cite here, but Jimbo and Miwa were certainly aware of things generally. So for the class of problems that we're concerned with, Brubaker, Bump, and Friedberg had studied these row transfer matrices for the 6-vertex model that are free fermionic and are related to the quantum group GL11. This is a Lie supergroup. And without the Q deformation, relations like I just showed you were found by Brubaker and Schultz. And there's similar facts that were found by Paul Zinn-Justin. There may be other literature that I should be mentioning here. I have a feeling that there's something involving Wheeler that that I should be citing. Does anybody want to comment? Ben or somebody?
There's a lot of good papers by Wheeler, but I don't know any that are exactly in this direction.
Okay. So anyway, Zinn-Justin, I don't know if this is in a paper, but he had some slides where he did stuff like this. So we expect that we'll be able to upgrade the story to GLRN. And I hope that I've convinced you that this is interesting. These row transfer matrices came up, for us, they came up in the theory of metaplectic Whittaker functions, and for other people that have talked in this seminar, such as Siddhartha. Now, if you want to study Iwahori Whittaker functions, then you need this this supergroup. So this so this story should have a supersymmetric version, which is more interesting than this one. The colors that appeared in this paper, if you look at our recent paper, are actually super colors. There's one actual color, and it's just the vertices that were labeled plus. So in the more interesting examples, this story should be quite a bit more interesting. I hope it's not too interesting. Anyway, that's all I have, but I can answer questions, and I have my iPad here in case I need it.
Let's thank Dan.